Hello everyone, I'm Horton, and this is Great Snake Variation Programming with Python Chess. To start out, I just want to say how excited and grateful I am to be here with all of you at Pytexas. It's been a long time since I got to go to an in-person conference. It's been a long time since I got to speak at an in-person conference, but I was at the 2019 Pytexas, had a great time, and so I'm really happy after all of this to be back here with you. And so you might all be wondering, why this talk, chess at a Python conference? I promise you there's something here. And the main blame, I would say, falls on the Queen's Gambit. I don't know if anyone else watched. I was definitely one of those people who binge watched this during the pandemic and got very into online chess. Now, I had played chess before as a kid. Yes, that's me as a kid before the gray hair set in. And I had done pretty well playing chess as a kid. This is actually a picture of chess trophies that I asked my mom to send me for this presentation. But most importantly, I learned how to beat my dad at chess using this book, which is actually a great book. If you're learning chess, highly recommend it. I did finally accomplish that. So I knew something about chess, but after about 5th grade, I had other interests, and I didn't really play chess much after that. I didn't really play seriously for about 16 years until the Queen's Gambit came and the pandemic hit, and all of a sudden I decided to dive back in. So I created an account on Chess, which is a free and open source tool, a free and open source chess server. It's a great thing if you want to play online with other people. And I dove right in, and when I say that, I really dove in. So here's a little bit of stats. So I started in November 2020, and that is at least the graph until July of 2021. I played almost 1,700 Blitz games online, and unfortunately, Chess also tells you how much time you've spent on it, and mine came out to over 19 days, which I did the math for this talk, is about an average of 30 minutes per day, every day since November 2020. I can say sometimes it is more than that, very often more than that. So I really got back into playing chess. I love playing chess online. Eventually I also got back into playing in-person chess at tournaments, which led to me having this very hilarious rating graph where on this side you can see was the single rated tournament I ever played as a kid, and I was rated 914 in 2004. Then you can see a 16-year gap where I played no chess, but the way they render it, for some reason, it has me steadily getting better at chess over that time, despite playing no chess. And then here is where I started playing chess in person, and basically after 1,700 Blitz games online, I was able to make very rapid progress once I finally returned to playing in person. And eventually, I started asking myself, can programming help me in training for chess? Can it help me analyze my games? So by day, I am a machine learning engineer, and so when I was approaching this problem, I thought, well, I have a lot of data. I have almost 1,700 games on Chess, which is the account I told you about. I have over 2,700 games on my chess.com account, which I did not mention up till now. So that's a lot of chess games, which in this case means a lot of data to analyze and maybe some interesting things that I can learn. And I was already inspired by some software tools that existed that I found useful. One of them was this thing called Opening Tree. So this will load your games from a given website and allow you to interactively explore different openings that you've played, ways your opponents have responded. It's a very useful tool. But I found that it couldn't always answer all the questions that I had. I wanted to go further, and so I decided, how can I write a program that does things like this? So I opened up PyPI, or as our keynote speaker called it, the magic shopping list of Python. And thankfully, I found what I was looking for, which was Python Chess, a chess library for Python, which was exactly what I wanted. And that is how this story started. To give you an idea of how this talk's going to go, to start off, I'm going to do a brief history of chess and programming. Then I'm going to dive into the API and usage of this library that I found and came to love called Python Chess. And finally, I'm going to go into a little bit about the applications of Python Chess, how I used it, some interesting ways I've seen other people use it. And I do want to underline, after all this, that I think my main idea for this talk is not to teach you something about chess, because some of you might be interested in chess and some of you might not care, and this is a Python conference. So what I really want you to take away in the end is that chess is just one interesting problem, it's one interesting domain where we can apply Python, we can apply programming principles, and that can teach us something even if you don't really care about knights and rooks and pawns. And to start off, that's why I want to give you a little bit of a brief history of chess and programming, because I think there is a lot of background to say that chess as a problem can teach us something about programming more generally. It started off maybe not so well with this contraption in 1770, which was supposedly a robot that could play chess by itself. People at the time didn't know that there was actually someone sitting inside of it manipulating this robot, and it made a grand tour of Europe and many places and defeated some great chess players, and people didn't necessarily catch on. And this does actually live on with some legacy in our current tech environment as the name of, it also lives on as the name of an Amazon service, Amazon Mechanical Turk, which you can use. So a second figure in the history of computer science and programming who got into chess was Alan Turing. I'll keep going. And in 1948, he wrote what is one of the first computer chess programs called TURING. Co-wrote it, there was another person. And the problem for Alan Turing was at the time there were no computers that could execute the complexity of this program that he designed. And so the only way that he could play it was to actually execute the algorithm on paper. And so there's one recorded game of him playing as the algorithm against a human, where he's actually writing out the calculations on paper, and it took about 30 minutes per move, which is not very efficient or probably very fun if you're the human on the other side. So he was maybe a little ahead of his time with this program. Another big figure in computer science, Claude Shannon, was known to have a great interest in computer chess. He wrote a very influential paper on it and later designed a machine, a robot that could play chess. Due to the technical limitations of the time, this machine you see here, it could only handle positions of up to 6 pieces due to the computational complexity, but still was quite an accomplishment. And he has a quote from this paper that I really liked as I was putting this talk together. He was talking about the problem of chess programming, and he said, perhaps it's not of practical importance, but he basically thought, by tackling this problem of programming chess, maybe we can make some headway toward larger problems. And he had in his mind big AI problems of translation and other things. But I think that this is a really fascinating idea that by learning something about this domain, by tackling this, we can go on to learn maybe bigger, better things. So another big figure in computer science, Ken Thompson, who created Unix, later in his career would co-create a language called Go. In the 70s, he was working at Bell Labs, and he came up with the software for this contraption called Bell in 1972, and this is one of the early champions of computer software championships at the time. And finally, I don't think I could complete my historical review of chess and programming without mentioning this big event in 1997 when IBM built this machine called Deep Blue, and it finally defeated Garry Kasparov, who at the time was the world chess champion. And this was the first time that a machine had defeated the human champion of chess. So this was kind of a big turning point in chess and programming and technology. So that's a little bit of an idea of the history of how chess has kind of influenced programming and drawn the interest of some people who went on to do or were doing great things in general programming and computer science. So with that out of the way, we'll get into this library. How can you do things with chess using Python? I mentioned that there's some programming principles that you can learn by looking at this library, and I wanted to mention a few of them in particular. So data parsing, object-oriented programming, very important. Data structures and algorithms, design patterns, and finally, communication protocols. And I'm going to go through examples of how you can see all of these things in the Python chess library, and basically how you can learn to use it by looking at these different principles. So, if you've done data parsing in Python before, you've probably used pandas, and you know that it provides a nice API for taking a structured data set, for example, a CSV. You can read it in, you can get it as a data frame, which then has a nice API to allow you to further manipulate the data, do any of the calculations that you want to do. Chess has a similar thing. It has structured data in this form, which is called PGN. That was a standard that was put together way back in the day in 1994 as a portable protocol for sharing chess games. And it lives on until today. This is the main format in which chess games are represented for processing. And similar to how Pandas has the ability to read a CSV, the Python chess library allows you to read in a PGN file. So here you can see, if you have a PGN, you can read it in and you get a game object. And that is going to allow you to do further analysis. So the next question might be, what is the game object? And that leads us into the next topic, which is object-oriented programming. And some of you may have once been subjected to programming interviews that make you do these kinds of problems. Maybe you've even had to implement chess in the stress of a 30-minute interview, or maybe some other kind of object-oriented game. So in this case, chess can be thought of as several classes. So an important one is piece, obviously, move, board, and game. These are all different classes with different functionalities that can help us represent chess as a whole. So I'm going to go through these classes. Some of them are fairly simple, some of them are fairly complex, and explain basically their APIs in the Python chess library and some of the interesting methods. So a piece is fairly simple. A piece just has a piece type and a color. It's essentially a data class that is holding these two things and representing them. A move is similarly fairly simple. Basically just has the square you're moving from, the square you're moving to, and then the piece you might be promoting to. That's in the case of moving a pawn. You can turn a pawn into a queen sometimes, so you want to keep track of that. And here it's referring to squares. And in this library, squares are also represented fairly simply. The square type is just an integer type, and all of the 64 squares on a standard chessboard are just assigned to unique integers, so they can be referred to 0 to 63. So then we get to board. And board is definitely the most complex class in the whole library, and you'll usually see that in chess programming. Most of the functionality will be represented on the board. And some of the things that it allows you to do is move generation, calculation of whether or not the particular position has completed the game. A bunch of stuff is packed into board. I looked at it in the library. The board class has over 2,300 lines of Python, so it's a whopper. It's a huge class. There's probably something you could say about that, but that would probably be a whole other talk. But most of the functionality lives in this class. There are a lot of interesting methods, and I just picked out a few that I thought were useful or interesting properties and methods of board. So some of the simple ones, you can check whose turn is it. You can check like what move you're on, which full move number is like what we think of as moves. So 1, white will move, black will move, 2, white will move, black will move again, and so on. So these things are represented on the board class. This one is outcome, and this actually represents like a huge percentage of that 2,300 lines, because calculating whether or not a chess game is over is actually extremely complex. Obviously, most people know about checkmate, stalemate, but there's all sorts of rules of like threefold repetition, so if you reach the same position 3 times, someone can claim a draw, and calculating that actually is like pretty complex. You have to go back through all the positions and see if it's been repeated. So this is a real big part of the complexity of programming a chess representation, is getting this right and knowing whether the game is over and how it finished. And these are some of the ones I picked out that I think are just like funny or interesting. There's checkers, which does not do what you think it does. I really thought this was like an implementation where you could just call this and all of a sudden you're playing checkers and not chess. That's not what it is. It's just finding all the pieces that are currently putting your king in check, which is kind of an interesting problem. And then the other one I thought was kind of cool is irreversible, so you can pass it a move, and it'll tell you if that's the kind of move that you can't undo. So in the case of like normal chess, moving your pawns forward, you can't undo that because they don't move backward. There's some things around, if you move your king, you won't be able to castle. So this is another interesting one where there's a lot of logic, domain-specific logic in there to say, okay, is this a move that someone's going to be able to take back or not? So I mentioned data structures and algorithms, and when we look into the classes that are used to implement the chess functionality in this library, you can see the use of some common data structures and algorithms. So for example, the moves that are made are represented as a stack, and the board class provides common methods, pop, peek, push, and you can also clear the stack. And if you look into the implementation of one of these methods, it's also interesting because it's actually holding 2 stacks on the class. There's a stack of moves, and then if you look at the implementation, there's also an internal stack of the board representation after that move, so that in processing you can know not only the moves that were made, but you can also go back through and see the resulting positions. And the game class is actually a tree of moves. So there's a game node, and they can point to various other game nodes, and that's how you represent a game, which is a very flexible model and useful because when you think of a game, you might think like just a set of moves, and then why isn't it like a list or a linked list or something? But in representing chess games, people often want to add variations. So then one move maybe could be followed by another move, but then there's a variation that someone wants to consider. And so that's how you get this tree structure. Off of each move, there could be several possibilities. So the game is represented as a tree of nodes. And this is the basic of a game node. It has a pointer up to its parent, and then a list of variations, which in like the general tree structure would be the children. And there are also some interesting methods on this that allow you to traverse the tree in different ways. So game would give you the overall game, which means going all the way back up to the root node of the tree. End is kind of the reverse, so it's going to follow all the way to the end of the tree down the main line. And in that case, this means that it's going to take the first child of each node. And the mainline method also gives you an iterable of all the nodes basically between this node and the end. So those are just some methods that are useful in traversing this particular tree, the game tree, in a useful way. And another thing I mentioned was design patterns. There's going to be a whole other talk about this later, but there is a design pattern in this library that I thought was pretty cool. It's the visitor pattern. So the visitor pattern is basically a way to specify a function that you want to run on each element of a data structure, but you don't want to add that to the class. So in this case, we have our game nodes, but maybe we don't want to have to modify game node for every operation we might want to do on the node. In this case, there's a visitor class, and what the visitor class allows you to do is specify for each node I want to run a particular function. And there's one simple example that's built into the library, and this is like string exporter. So this is the visitor. The visit move method is basically a method that's called on every move in the tree. And in this case, it's basically just for each move, creating a string representation of that and appending that on to basically a running string that it's keeping. Another, I found this very interesting, is the use of standard communication protocols, which in general programming I would say is very useful if you've ever had to collect metrics. You might have used statsd, which allows you to basically collect metrics and send them on to Datadog or any other collector in a very standardized way. One that's come up in my own work very recently is this library called kserve, which provides a standard interface for getting model predictions, regardless of the underlying implementation of the model. These are like a couple of standard protocols. I think in programming, we can agree that this is like a super important thing, and in chess it's no different. So in the chess world, there's a common protocol for communicating with chess engines, which means that if you want to write a program that talks to an engine, you don't have to write a different program for engine A or engine B. Someone came up with a standard protocol, and it turns out it's very Unixy, which is kind of funny, but all the communication goes over standard in and standard out via text, and that's kind of the protocol. It's called UCI. And it's a fairly complex spec. This is like one example. This is the go command. And this is used to actually run the engine. There's a lot of different options, a lot of parameters. And you can imagine that if you had to implement a client for this, that might get very cumbersome, and you probably wouldn't want to do it if you're just like playing around and want to like run a chess engine. So the cool thing is Python chess also has an interface for interacting with any chess engine over this standard UCI protocol. So this snippet is an example of basically starting up Stockfish, which is a commonly used engine, and then allowing it to play a game of chess against itself, giving it a limit of 100 milliseconds per move. And I should also mention Stockfish is also free and open source software, which is super cool. It's a super, super powerful chess engine. And I wanted to go back to this kind of historical point, which is in 1987 when Deep Blue beat Garry Kasparov, this was like a huge historical moment requiring years and years of effort by like a huge team of people. And I just think it's really cool that in 2022, through open source software, you can now access an engine that's way more powerful than Deep Blue on your laptop using these open source tools. So Python, Python chess, and Stockfish. I think that's a really cool thing, and kind of shows the power of technology and how much it's grown. So this is the class that is in the Python chess library that provides you access to an engine. It has two main methods. It has play and analyze, which do slightly different things. Play is basically going to play the board that you pass it. Analyze is slightly more flexible, so you can ask for multiple moves, and it'll basically just return a dictionary of information. So after going through kind of the internals of the library, the API, how to use it, I wanted to end by going through two applications of what you might want to do with this library. And I will say, this is the more like chessy part of the talk, but I hope that it'll also be interesting to everyone. So we'll start with an application that I wrote myself, and it has to do with opening training. And basically in chess, there's a concept of an opening book. And it's basically, if my opponent plays X, I'm going to play Y to any various depth. So you might have, you always play E4 as your first move, things like that. And as an example, this is a representation of one, don't tell any of my opponents. This is like the beginning of my opening book. So I might always play B3 as white. This has various responses. They can make various responses I would make back. It's basically this tree of moves that shows what I would play in a given position, starting from move 1. And as you play more games, as I play more games, the questions I want to ask myself are, like, how far am I making it in before I kind of end up out of book, as they say. So you're having to play kind of on your own with no preparation. And when I reach those positions, am I the one messing it up? Am I forgetting the moves I should have studied? Or is my opponent playing something unexpected? And maybe, like, what does the engine think about that? Like, am I getting out of book because my opponent is playing terrible moves? And then maybe I don't need to study those moves because they're obviously bad. So these are a bunch of the questions I had. And like I said, I had a lot of data to work with in my games, so I wanted to do some analysis. So I ended up with implementation that basically uses two classes of visitors. It uses the base visitor from Python chess, and this one is a fairly simple implementation basically on each move, it's getting two things and it's storing them. It's getting the fen, which is a representation of the position, a unique representation of the position, and then the move that was made in that position. So this is basically going over my whole opening book and saying, at each position, what move can be made. And those moves are represented as a set, because in some positions, usually you'd want to have only one move in each position for your opening book, but obviously your opponent could play many different moves. And so this visitor will go through my whole opening book, which is represented as a PGN, and collect those things. And once it collects all those things, this is like kind of the representation I get, which is what I wanted. It's a dictionary that maps keys that are positions to a set of moves. And so this is the same example I showed before. So at the start, I will always play B3, hence there's only one move in the set. The position after that is my opponent's move. There's many moves they might make that are in my opening book, so that's the second set you see there, and so on through all the positions that I have represented. So once I have that, I create another visitor that basically will go over a set of games and determine at what point in the game did I reach a position that's not in that dictionary. So I've collected from my opening book all the positions that I, in theory, should have studied and learned what to play here. And so now I go through all my games and I say, take the fen, which is the position, and the move, and say, if this position is in this dictionary I just created, is the move in the set of moves, or is it not? And if it's not, then I add it to this list, basically of divergences. And over a series of games, you can collect many of these divergences. So once I run this visitor on a set of games, you would end up with something like this, which is a list of kind of metadata about places where I ended up outside of my opening preparation. And so for the first one, you can see was kind of my fault. So I played as white, and on the third move, I played d4. And in my preparation, I was supposed to learn to play bishop d2. But then the second example you can see is where my opponent diverged. So they played a move that I never expected. And so maybe that's something you want to go study. And once you create a bunch of these for, say, 1700 Blitz games, you can start to aggregate them. So you can start to get a sense of how far on average do I make it in the game, how often am I the one messing up versus my opponent, things like that. So this is pretty useful if you're working on learning a chess opening and you want to figure out how are you doing at actually trying to learn that and remember the moves you're supposed to play. So I have a second application, which I think is very interesting, and it's the application of chess puzzle generation, which before all these like tools, software tools, it was pretty hard. You had to do it manually. You had to review a game. You had to say, okay, is this an interesting position? Like interesting by some metric. And then you had to go through and say, okay, did the people play this correctly? And kind of find a puzzle through very manual inspection. But it turns out the criteria for a puzzle can be generalized. And for a chess puzzle, you want to basically find a position where one side's chances shift very dramatically. So usually someone has made a mistake, and now someone can take advantage. And in order to take advantage, that player has to play a series of moves where they only have one move to play. Because otherwise, if there's a lot of moves, you can't really solve the puzzle. There might be like 5 solutions, and then it's really not that interesting. And after that series of moves, you have to have a measurable outcome. So that might end in checkmate, stalemate, or the gain of material. So this is an example of a chess puzzle that I just looked at this morning. I'm low on time, so I'll run through it quickly. But basically, I won't explain all the chess logic, but black here can take the rook, which is what I did. Now white has to take back the rook, because otherwise they'll be down a rook. They have no choice. But that means black can play the knight, which executes a classic tactic known as a fork. And in this position, the rook now can't protect the bishop. The rook has to go somewhere else, or be captured by the knight. Now the knight captures the bishop, and black is up a piece. So this is the little puzzle. in this series of moves, there was really only one move for black and one move for white in order to arrive at this result. And so there's a really cool open source tool called Chess Puzzle Maker that basically puts these criteria into an algorithm that's expressed in Python. And it uses Python chess. So how is it using Python chess to find these puzzles? So there's really two functionalities that I wanted to look at. This is how it finds puzzles, and I basically just wanted to show that here it's using the game, it's traversing the game tree, it's using some of the methods that I mentioned that are important in the Python chess API to basically go through the game and examine the positions. It's also using the engine protocol to communicate with Stockfish in order to evaluate the positions and get the best moves. So, to wrap it up, I think Python chess is a super cool library. I hope that you learned something, maybe not only about chess, but about Python and programming. And as my final slide, I wanted to show a simple program. So this is using Python chess to play just two moves. This is an opening c4, g6. This is known as the Great Snake variation, and I just thought it was a nice way to show that Python and chess can go well together. Thank you. My Twitter is wdhorton. If you want to play me on chess, there's my account. You can send me a challenge. Thank you all.